Hello, welcome back to Dinosaurs. We're going to keep rolling through Module 1. Again, here's the schedule. Today we're going to talk about fossil record, or I should say lack of fossil record. Most of the fossil record is actually gaps, and we'll talk about the consequences of that as we're trying to reconstruct the past. We're going to talk a little bit more about evolution and how we classify organisms and how we group them together and how they change over time next week and towards the end of this week. But that's the kind of the schedule there. So keep on pace, keep doing what you're doing, follow along on the course schedule. If you're confused with anything, post up on discussion board. So a couple announcements before we get into today. Okay, so something that I probably should have started doing earlier in the class, but we're going to be doing this going forward, is kind of before we get into today's material, kind of reviewing from last time. So this is a review of geology / stratigraphy, which was last course. So which of these geologic events is the youngest? So take a look at that cross section. I'll give you a couple seconds. Remember law of superposition? Remember law of cross-cutting? There are no inclusions shown on here, but remember the law of inclusions. That's how we relatively date things. We can't absolute date the sedimentary rocks, but we could absolute date this igneous intrusion here and get a good bracketing age on those. So which is the youngest event here? It is S. So S, this layer up here, this sand, is the youngest unit. Why? Because it's on the top. And it's also cross-cutting, it's eroding these other units. It's removed part of T, it's removed part of G, it's cross-cut those, it's eroded it. So S is the youngest event here. N is the oldest, followed by A, because A is on top of it, followed by T, because it's on top of A. And then G cuts across these three, which means it's younger, but it doesn't cut across S. It stops at S. So that's how we put these things in relative age order. Next thing, which of these processes drives plate tectonics? So we have a spreading ridge here in the middle of the oceans, new crust being created, moving out. Over here we have a subduction zone where old crust is subducting and sinking and being destroyed. What process is it that drives this loop here, these cells? And of course the answer is convection. So convection is what drives these hot mantle material here, heats up, becomes more buoyant, it rises, it pulls the plates apart, it cools, and it sinks. It heats up, it rises, it moves, it cools, it sinks. Convection cells. Okay, so what is a fossil? So all of today is about the fossil record. So what's a fossil? So a fossil is any kind of evidence of the past that's contained in the rock record. It doesn't have to be what we think of as a fossil, like the bones. I'll talk about that in just a second. But generally, fossils are more than 1,000 years old. Things like bones, leaves, shells, etc. And it's usually the hard parts that are fossilized. So I'm part of a fossil forum on Facebook, and a lot of people will post up like pictures of rocks that kind of look like a snake's head or a dog's head or something like that. And they'll be like, is this a fossil? And the answer is almost always no, because if something looks like a living animal, a full living animal, with the soft parts and everything preserved, it's probably not a fossil. It probably just happens to be coincidence, because usually only the hard parts are preserved. Like, for example, the bones here, all the musculature, all the skin, all the organs, any hair, any feathers, any other ornamentation that was part of this T-Rex is gone. Only the hard parts, the bones, are left behind. And so that makes it very challenging to reconstruct what the entire organism looked like. We can see its morphology in the skeleton, but beyond that, we have to sort of rely on looking at analogs and trying to reconstruct. There's also this idea of body fossils. This is a body fossil. This is a body fossil here. Body fossils are fossils that are the remnants of the actual organism itself, parts of the body, versus trace fossils. Trace fossils are fossils of behavior. So this is a big old dinosaur footprint. Again, you see that kind of three-toed, very similar to a lot of the modern birds. What a coincidence, right? These are pretty big. So you can see water collecting in there in a puddle. And you can see the whole trackway here. There are no dinosaur bones here. This is not a body fossil, this is a trace fossil. It's a trace of an animal and its behavior, but the animal itself is not here. It may in fact be way down the trace, but we don't know, maybe, probably never know. Another interesting kind of trace fossil is dinosaur leavings. So this is a T-Rex loaf. So why would we look at dinosaur poo? Well, we can learn a lot from their leavings. So this is T-Rex. How do we know? Because it's so large. T-Rex was the only animal around that was that large, that was a meat eater at that time that could have produced this. So what can we learn from this? You look in there, you see the chemical composition, you see bone fragments in there. We can reconstruct kind of what it ate, what its diet was. We can't see the animal's guts from the body parts, but we can make inferences of how it digested things, what it was eating, based on, well, what comes out the other end. So looking at leavings, trace fossils, fossilized behavior is very important. And the word fossil just comes from the Latin fossilis, which means dug up. So we dig up these fossils. So again, this is a velociraptor here, one of our favorites. You see these big old famous hooked claws. And again, they weren't as big as on Jurassic Park. They were much smaller, kind of like turkey-ish sized. But if you've ever had a turkey coming at you, you know that they're pretty scary, and these claws are pretty nasty. So, so basically, as long as humanity has been around, we've been curious about what these things are. We talked about this earlier, where dinosaur bones may have been the inspiration for a lot of mythological creatures, like particularly dragons or griffins. But we've always been fascinated by these things that they called petrifactions. A lot of people had these curio cabinets, curiosity cabinets, and fossils were a very popular item to go in there. So the first like record that we have of someone suggesting that these were formerly living organisms was Xanthos of Sardis in about 500 BC. So kind of very early on, so at least some people were saying like, hey, you know, these things kind of look like the remains of organisms that we see today, or at least vaguely like today. Maybe they were living, maybe they weren't always rock. Aristotle kind of continued on this and kind of suggested that they were living animals and they kind of crawled into cracks in the rock and then they just kind of got stuck there. And then DaVinci in 1500-ish, he was climbing around in the mountains and he noticed, wow, there are seashells up here way in the mountains, like way in the top of the Alps. Why are there seashells up here way above sea level? And again, this goes back to plate tectonics, the geology lesson from last time. The Earth is always moving around and shifting, and things that were deep ocean are pushed up. The Himalayan mountains, the highest mountains on Earth, the rocks at the tippy top of the Earth are marine limestones with marine fossils, marine shells in there, because those rocks have been tilted up and formed. So how did they get there? Again, early on, a lot of people thought maybe the devil put them there to like trick us, or it was a result of the great flood that buried these things very quickly. Some people made up other explanations, like for example, some fossils were sometimes called toadstones, and they were thought to be like these lucky rocks that like were inside of toads' heads and they would collect them. Or they were called, for the example, this is an ammonite, an ancient cephalopod, kind of like an octopus with a shell, a nautilus sort of, not really, but close. They were called snake stones because they look like a curled up snake, so much so that some people actually carved little heads on there, little faces, to kind of sell the illusion, and of course increase the value as a curio, a curiosity. So people were always kind of fascinated by fossils. It wasn't until Nicolas Steno in the 1660s, again, Steno is one of the people that really drove home those principles that we talked about last time, the superposition, cross-cutting, inclusions. But he was also the first to propose that the rocks were not always rock. The sedimentary rocks that make up the fossil record, those pages of geologic time that if we know what we're looking for, we can read them and reconstruct the story. They were not always rock, they were sediment A mudstone was at one point mud, a shale was mud. A sandstone was at one point sand. It was a soft sediment, these broken up fragments of rock, and it was only later lithified into a rock. So the animals that were living on that sand, living on that mud, some of their remains got stuck in there when it was still soft sediment. That sediment was buried and squished and squeezed and cemented and lithified into a rock, and in some cases the fossils were preserved in there. And again, he's the one that kind of came up with this. But one of the big things here was there were these curios called tungstones that they thought at the time were the tips of dragons' tongues. So there's no dragons around anymore, but there's all these weird ancient remains. So where did they come from? Well, they must be dragon stones. Steno was the first one to recognize that, hey, these dragon stones look a lot like shark teeth. And so he found a modern shark preserved, a corpse, saw that the teeth, and he really just kind of did a side-by-side, was like, these aren't dragon stones, these are shark teeth. And that really started pushing forward that, you know, fossils are the remnants of ancient organisms, and they're preserved in the rock record, mostly not preserved in the rock record, and we'll talk about that in just a couple minutes. So why are we talking about this? Why are we having this class? Why are fossils important? Why are dinosaurs important? Why are any extinct animals important? Why do we care? They're long dead. They've been dead for 66 million years. What could we possibly learn from them? Well, one thing is biostratigraphy. So we talked a little bit about stratigraphy last time. Biostratigraphy is layers of life that are stacked up, and we can actually use them to date rocks. We know the time that those fossils lived. We can correlate rocks across. We don't need to worry about that so much for this class, but we use it a lot in the oil and gas industry to look at the different fossil contents and be like, this rock over here has those fossils. This rock way over here on a different continent has those same fossils. They must be the same age. We also use it for paleogeography. So if we look at fossil distribution, again, this was one of the major pieces of evidence for plate tectonics. These land-based organisms or freshwater organisms couldn't have swam across the oceans. We need to put the continents back together, recreate geography of the past, paleogeography, to make this make sense. Climate change is another thing. The evidence of the climate is locked in the rocks. Dry climates and wet climates produce different rock records, and we can analyze the rocks and the fossils, the different animals that are living there, to reconstruct the climate past. And if we know about the climate past, we can make predictions about the climate future, which is one of the most largest challenges that's facing us. They also record evolution. So this is, in this case, it's the evolution of horses, going from a 5-fingered ancestor to the modern hoof. And we kind of see this slow transition over time. We can reconstruct evidence of evolution from the rock record, the fossil record. We can investigate our origins. So this is Lucy, the famous Australopithecus afarensis, one of our most ancient ancestors, possibly the first bipedal hominin, the first that stood up and freed up our hands for doing things. We can also see behavior and reconstruct behavior of ancient organisms and what life was like back in the time. What did T-Rex do? What was its diet? Was it a hunter, an active hunter? Was it a scavenger? How can we figure that out? We need to look at the fossils. And then the last one is extinction. So if we look at ancient extinctions, if we look at extinctions in the past, it can tell us something about what those causes were. And in theory, we would like to avoid that. So one common theme throughout geologic history is that mass extinctions coincide with major disruptions in the carbon cycle. What's happening today? A very major disruption in the carbon cycle, anthropogenic in this case, human-induced disruption in the carbon cycle, burning fossil fuels that should have stayed underground and putting millions of years worth of carbon into the air in hundreds of years, leading to a lot of animals going extinct. Possibly, some people say we're in a 6th mass extinction today. We'll see. Hopefully we won't see. So that's why fossils are important. So how are fossils made? If you look at an organism, There are hard parts of the organism, like this T-Rex's skeleton, and there are soft parts of the organism, like our skin, our muscles, our hair, or our lack thereof, um, ornamentation, even, I suppose, clothes. Obviously, dinosaurs didn't wear clothes, but hard parts versus soft parts, which is more likely to be preserved? Again, if you look at this Tyrannosaurus Rex skeleton here, the bones are preserved and nothing else is. Did dinosaurs have feathers? Did dinosaurs have hair? What was the musculature of the dinosaur? How muscly was this thing? Did dinosaurs have lips to cover these big teeth? These are questions that are very difficult to answer because really we have mostly the skeletal remains. We'll talk about all that other stuff later in the course and how we might make good guesstimates of how that's done. But again, mostly it's the hard parts. So what's the impact on the fossil record? We have very good, strong evidence for animals that have a lot of hard parts, and we were able to reconstruct their skeletal morphology, the skeletal shape, but it's very difficult to reconstruct the soft parts. This is an ichthyosaur. Remember, not everything that ends with "saur" is a dinosaur, so ichthyosaurs are not dinosaurs, they're marine reptiles. Very much looks like a fish or a dolphin. Again, it's not a fish or a dolphin either, it just superficially looks like one. An example of convergent evolution, which we'll talk about next week. Why am I showing this in the dinosaurs class? This is just a really good example of the hard parts here are preserved. You can see the bones, you can see the teeth. The soft parts, kind of the outline of the organism, are preserved as just a carbon film. This is an exceptional level of presentation here. You can actually see the outline of the organism's body with this thin carbon film. The skin's long gone, the muscles are gone, the guts are gone. Only the hard parts are truly preserved, but the soft parts are sort of preserved as this film. And in many ways, it gives us glimpses into the soft parts. So it's not always just the hard parts that are preserved, but it's very uncommon to see soft things preserved in the fossil record, which also means that there are a lot of organisms that are way more likely to be represented in the fossil record than others. So for example, this jellyfish, the fossil record of jellyfish, of worms, of animals that have only soft body parts that do not have a skeleton, it's very scarce. Jellyfish fossils are incredibly rare, and you see that this body fossil is basically just an imprint with a carbon film. There's not a lot we can really tell from this organism other than its overall kind of shape. And so remember that the fossil record is biased. It's biased towards critters that have hard parts. Again, I'm not a vertebrate paleontologist that studies vertebrate animals like, for example, this ichthyosaur or this human. I study invertebrates, so a lot of marine things like mollusks, cephalopods, trilobites, because they have hard parts that tend to be preserved in the fossil record a lot. If you go to a lot of the rocks around here, you'll see little seashells in there preserved because of the hard skeleton, the hard exoskeleton of those organisms. So the fossil record is biased. If you think about a human skeleton, which bones are most likely to be preserved? Well, rib bones are very long and slender. They're very likely to be smashed up. Really the hard, durable bones like jawbone, teeth especially, fingers, phalanges, they're relatively small, but they're relatively robust for their size. Those are what we find. Hip bones, scapula, rib bones are generally smashed. Vertebrae are pretty tough, but there's also a bias in the kind of bones that you find. Skulls are often smashed into pieces. So we're biased in that respect too. So how does something become a fossil? Well, let's talk about that. So there's a couple different ways, but it all sort of involves, first of all, unfortunately, the animal has to die. So the animal dies. It's pictured here as being dead in water because that's a very good place for you to possibly be preserved. The animal dies, it sinks to the bottom or it lays on the bottom, and it's slowly buried, and the skeleton's buried as bone. The layers build up over time. They might even be tilted in this case here. And eventually the sediments erode away and we might be able to see the bones here and analyze the fossil. What you'll notice is that there are a lot of bones that are missing. It's not in perfect order. It's kind of a puzzle that you have to put back together. But these are the preservation ways that you present things. So the first one's unaltered remains. So unaltered remains are organisms that have original tissue intact. So these are things that still have skin, still have hair, in some cases still have muscle, internal organs even. This is incredibly rare, and especially so in the dinosaurs. But it's pretty common in, like, quote unquote Ice Age, Pleistocene organisms, for example, the La Brea tar pits or Ötzi the Iceman. Amber preserves things perfectly. This is sort of a glimpse into the Mesozoic world with the fossil amber. It's not quite the same as they say on Jurassic Park, but you know, whatever. Peat is another way, or ash. So like in Pompeii, those human remains are sort of preserved there. Or lake sediments. Lake sediments is a good way to preserve organisms with relatively unaltered remains. These are some examples from the permafrost, a little baby mammoth here, and a dire wolf pup that are basically mummified. These are unaltered remains. You can even examine the stomach contents in some cases. We don't get this lucky with dinosaurs. Dinosaurs are generally preserved with permineralization. So that's minerals are deposited really slow inside the cells of dead organisms. So you have the cell structure of the dinosaur bone. Over time, the pores in the bone are filled in with minerals that are floating around in the groundwater, dissolved in the groundwater. The cell walls kind of remain intact, and the crystals sort of grow in to fill the spaces. And this can preserve incredible amounts of detail. It's very common in dinosaur bones, so this is a permineralized skeleton. That's why dinosaur bones look like rock, because they really are. It's not the original bone material. The bone material has been replaced slowly and precisely with minerals that deposit over time. Same thing with petrified wood. None of the original wood, lignite, actually remains here. It's been replaced over time by minerals. And again, you see the high fidelity at which it's been replaced. You can actually see the tree rings in here in the minerals. So the original material is gone, but that doesn't mean the detail's been destroyed. In many cases, it is preserved. Another way is to recrystallize. This is less common for dinosaurs. Bones don't necessarily recrystallize, but it is very common in marine invertebrates. So they build their shells out of aragonite in some cases, or calcite. Over time, that mineral can recrystallize into just larger crystals of the same mineral, sort of a pixelation process where you sort of lose some detail, or it can be transformed into a completely different mineral. So this is a beautiful abalone shell. A lot of times you'll see people use these as incense burners because they're so cool looking. This is an aragonite abalone shell, a modern shell. If we were to bury this in the rock record, that beautiful kind of mother of pearl sheen would slowly degrade as it changes into calcite. So this is recrystallization. We don't have to worry about this so much for dinosaurs. Mostly we need to worry about permineralization. Dissolution or replacement is pretty similar, where the original skeleton or shell is dissolved completely away and it leaves a void, and that void may or may not get filled in. In this case, this trilobite skeleton dissolved away and it was replaced by pyrite, by fool's gold, and we have this pretty great metal trilobite. It's really cool. This is from the Beecher trilobite beds in southern New York State. So this is a New York State fossil, and you see the legs are preserved, the antennae are preserved in some of the specimens. Some of them even have eggs and even gills preserved. Incredible detail from the dissolution and replacement with pyrite minerals. Here is a bivalve, a clam, that you can see the inside of the shell, you can see kind of the outside of the shell, and then there's a gap in here. That's where the shell material was. The shell material has dissolved away, and it's left this mold, an open void space, very similar to like if you're making chocolates, you have an open mold you pour chocolate into it, and you pop it out, and you get a cast of the original thing. So this is a mold where the stuff is gone, and a cast would be if this filled back in. This is essentially a cast of the trilobite. And then there's carbonization. So living things are carbon-based living things, at least on Earth. So our soft tissues are made out of carbon. In a lot of cases, again, most of the time we find hard parts preserved, the skeleton, and we don't get soft parts preserved at all. The most common way that soft parts are preserved, though, is as carbon films. So this is a carbon film of, I think these are Pennsylvanian, but they're leaves. These leaves were buried in the sediment. They were preserved as carbon films. All the leaf material has been reduced to a carbon film. If you think about coal, coal is just a big stack of this carbon film stacked up from all these leaves. It's not dinosaurs. Same thing with oil and gas. Oil and gas is the cooking of these carbons into hydrocarbons, oil and gas. It's not from dinosaur corpses. It's from plant material or even microscopic plankton. It's not dinosaurs. Dinosaurs are an immeasurably small percentage of fossil fuels, basically none. It's mostly from this carbonization of plant material, especially microscopic plant material. But carbonization does occur in dinosaurs, and this is a very, very great example. This is a Sinosauropteryx, and you can see that the feathers, these little filamentous feathers, are preserved not as feathers, but as carbon films. You can actually even see on the tail the striping. There's like a dark stripe, a light stripe, dark stripe, light stripe, dark stripe, light stripe, dark stripe. Some of the coloration is actually preserved here. And we can see that this was probably a striped tail, relatively small dinosaur with actually a pretty good coating of feathers, or I should say proto-feathers, over the body. And this is a very uncommon degree of preservation that gives us a glimpse into the soft parts. Some of the skin, some of the musculature, some of the guts are actually preserved as carbon films as well. Not a perfect record, but it gives us some glimpse into the soft parts of this organism. Very, very uncommon, highly prized by scientists because we don't often see this. So there's this idea, this process in paleontology that's called taphonomy. And taphonomy is the study of everything that happens to an organism from the time it dies to the time that it becomes a fossil and is collected and put into a museum, or incredibly more likely from the time that it dies to the time that it is not fossilized and it's never found and it's never put into a museum. A very small amount of organisms that live on this earth become fossilized and preserved for us to look at. That's one of the problems of paleontology. One of the problems of reconstructing ancient organisms like dinosaurs is that very few of them were even preserved. Even fewer of them were actually found, and even fewer of those were actually analyzed. And so taphonomy is the study of these changes. So there's the life assemblage, which is all of the critters that are living, all of the big critters like the dinosaurs, all the way down to the little critters like worms, insects, bacteria. And then you go from the life assemblage, all of those living animals, and you have to, what we see partially is the animals that are actually able to be preserved in the rock record. And so like worms decay away. Microfossils are very unlikely to be preserved. That's the death assemblage. Of that death assemblage that may be preserved in the rock record, very little of that is, because it's kind of destroyed in the process of lithification. And so at the end of the day, the stuff that actually makes it into a collection, the stuff that survives these taphonomic processes, this degradation of the fossil record over time, is a very small percentage. And so the science of paleontology, of paleoecology, trying to take what we know from the fossil record and trying to restore to the whole big picture, it's very complicated. We use actually forensic taphonomy in forensic science to sort of reconstruct the time of death. So if we find, in this particular book, it's the postmortem fate of human remains, what happens to a human body over time? How quickly does it move from a full, flesh suit all the way to disaggregated bones? How long does that take? We can actually use that to decide, like, okay, this is the remains of a relatively recent, or is this a cold case, or is this fossil remains, ancient remains? And so, like, this is an example of a vertebrate of some kind just laying out on the ground, and you see it's disarticulated, the bones are scattered about, not everything's here, the head has been carried away, maybe to be scavenged upon. But taphonomy is all the things that could happen between when an organism dies all the way to when we're looking at it in a collection. So what kind of things can happen? What are these processes? So there's kind of two different ways to look at this. One is like if you have an exoskeleton, and one is if you have a skeleton. So this is more for invertebrate paleontology. This is more for vertebrate paleontology. So dinosaurs are kind of over on this scale here. So we have these happy living critters, cute little trilobite, cute little gazelle, and unfortunately, they meet with an untimely end. So what's going to happen to their remains between the time that they've kicked the bucket and the time that we would be able to see them? So the first thing that can happen, well, some things are going to be biological agents. So we'll focus mostly on this list here. The organism decays, it decomposes, so to compose something is to put it together. If you compose a piece of music, you're making it, you're creating it. Decomposing is tearing it apart. The skeleton, the soft bits, decompose, disarticulate, break into parts. Scavengers can help this process. If a hyena or something comes along and rips off a leg and carts off with it, or a delicious head moves away with it, that's the scavengers are actively destroying that evidence. It wouldn't be hyenas back in the Mesozoic, but T-Rex potentially was scavenging carcasses. Think of how much damage this thing could do to a dinosaur carcass. All the intact remains there just scattered about. It could be just trampled or crushed. So think of all the massive organisms that are roaming around. Big old sauropod walking around, thump, 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 steps on a carcass, or even a buried carcass, crushing those bones. And then there's the mechanical agents, wind, rain, rivers. These things erode hard, solid rock. They also break down and erode skeletons. Again, if something's being transported in a river, if you think about like a deer or something that died alongside the river, if it starts being transported, it's going to be broken up into bits and scattered about, maybe so much that we're not even able to figure out what it was. It could also be eroded away, or it could just never get buried. The organism never gets buried, it stays out on the surface of the earth, and eventually it erodes into dust, and we never are able to find it. The last thing that could possibly happen is just random chance. Let's just say that this fossil survived all of these different processes. It's kind of rolling the geologic dice, and it wins the geologic lottery. It makes it into the fossil record. It's preserved into the fossil record. It's actually exposed at the surface so that somebody could happen upon it, but then nobody ever does. Nobody happens to walk down the creek during the couple days or weeks or months or years that it's exposed at the surface, and it slowly just erodes away and is never found. It survived 65, 66, 100 million years in the fossil record, just waiting for us to be found. It was finally exposed to light of day so that we could see it, and we didn't. And we lost out on that information that was preserved in that fossil forever. And so these are the processes from going from a living organism to what we can study and see. And a lot of information is lost along the way. A lot of individual specimens are lost along the way through these processes. So how do we preserve anything into the fossil record? Well, the best way to do it is we have an organism. In this case, it's a gazelle or an antelope or something. not a dinosaur, but dinosaur process would be very similar to this. We have a happy little living critter, and it meets its untimely end. It might be scavenged upon, it might be trampled upon. The weather erodes and breaks it. Plants can actually erode and break it. Bacteria, decomposers, fungi are breaking it down. And from this living organism, we end up with a living pile of bone, or a pile of bone. That pile of bone is buried in the geology. Tectonics could happen to destroy it. Erosion then exposes the fossils, and if it waits around too long, it destroys them. The best way to be preserved is be rapidly, gently buried before biological activity, before scavengers can break it up, before decomposers can break it down. And the best way to do this is to be buried in a low energy environment, like a lake bottom, where there's not a lot of waves, there's not a lot of wind, there's not a lot of anything. There's very low energy, it's a very calm environment. You're just slowly buried by mud, trickling down. There's no oxygen, so there's no critters eating the soft parts. This is the best way to preserve it. Now, it's not the only way, but the best way is rapid, gentle burial, so that you're buried in the sediments quickly before all of this other stuff can destroy the evidence. So dinosaurs live on land. How could they find their way out to very low, calm, slow waters? Well, the best way is probably the old bloat and float. So an animal dies near a lake shore or near a river, and over time, the decomposition of the internal organs creates these gases. You've seen roadkill on the side of the road with the legs straight up in the air and the body just swollen up because of the gases building up in there. That actually makes the corpse buoyant, and it can float in the water if it's able to avoid being scavenged by, like in this case, it's an ankylosaur. This is an ichthyosaur looking, maybe a tasty morsel that floated my way. But this land organism died on land, and it was floated out to sea, where eventually it pops, the gases escape, and it sinks to the bottom. One thing that was always kind of a mystery is, why are so many dinosaur skeletons found upside down? Why would an ankylosaur, these big, massive, armored tank dinosaurs, why are a lot of them found upside down? How do you flip over this big tank? Well, the best explanation is they bloat and float, and they drop, and then they're preserved by the sediment that rains down on top of them gently and covers them up. So what we see in the fossil record is that there's an environmental bias. Fossilization is very likely in most environments if the material remains intact and if it's buried quickly before it gets torn apart by all of those processes. So think about geology, think about all these different environments. Which environment is this more likely? So like a muddy lake, a muddy river, a muddy swamp, pretty low energy environment, not a lot of oxygen maybe. This is very likely to preserve fossil material. A sandy shoreline, waves go in, waves go out, waves go in, waves go out, pretty high energy. You see the fossil shells here, a lot of them are somewhat whole. Some of them are broken up though, because of the higher energy of the sandy beach. If it's a really high energy beach, a rocky environment, again, remember, the higher the grain size, the bigger the grain size, the higher the energy in general. Here, the wave action is very strong. Any bones along here are likely to be smashed up, broken, very unlikely to be preserved. And then the least likely is on land. So again, if you die on land, dry, open ground, you're not going to be buried very quickly. You're going to be exposed for a really long time. There are still places on Earth where it's a dry desert now, and there's whale skeletons just at the surface of the Earth from the ancient environment. They're hundreds of thousands of years old, and they're tens of thousands at least, and they're still exposed at the surface and slowly being broken down over time and not preserved in the fossil record. Being preserved on land is really unlikely. And this is unfortunate because, again, we've talked about pterosaurs, the flying reptiles. We talked about ichthyosaurs, plesiosaurs, mosasaurs. the marine reptiles, those lived in the sky and in the oceans. All of the actual dinosaurs, those are not dinosaurs, all the actual dinosaurs, those special branch of reptiles, none of them lived in the air or the water. They're all terrestrial based, where they're least likely to be preserved. And so a lot of the spectacular preservation is near lake shores, near rivers, where they're able to be buried quickly. So how likely is it that something becomes a fossil? The answer is not very likely at all, due to all of those factors that we just talked about. Now remember that some bones or some shells are more likely to be preserved than others. Something, again, that's very robust, like a jawbone or teeth, pretty highly likely, or at least more likely to be in there. An estimate that's commonly cited is that about 1 bone in a billion, billion with a B, is fossilized. So if we think about all of the entire population of the US, so what is it, 330 million people, something like that, we all have 200 some bones. 330 million times 200 some bones divided by a billion, it equates to about 60 bones. That's about a quarter of a skeleton. So obviously I don't want this to happen, but if everybody in the United States was instantly dead and tried to be fossilized, the results at this rate of preservation would be that 1/4 of one skeleton would be preserved in the rock record. So that's the likelihood that we're dealing with here. Now remember, that's an instantaneous slice. There's 330 million people alive in the United States today. Think about how many people have been alive in the United States in the last 250 years. Now for dinosaurs, think about how many dinosaurs lived for 200 million years or 150 million years. It's a lot of individuals, and so there's just more material that might be preserved, but it's really unlikely. 1 in a billion bones make it into the fossil record. So from that, it's estimated that about 0.1% of all species that have ever existed have entered the fossil record. Think about how little we know about all the species that live on Earth today that we can go directly observe. We find new species in the deep oceans. We find new species in the rainforest. We find new species everywhere, every day. Now think about all of this noise here. Only 1 in a billion of those bones is preserved. Think about how little we know about the ancient rock record. The fossil record is really not a record at all. It's more about the gaps, more of what's missing, and trying to reconstruct what's missing from the small amount of material that we do have. And this is just kind of a graph over time of bone material, shell material that was been tumbled along a river. They used a rock tumbler. If you were a kid, you throw jagged rocks in here. The barrel spins around with some sand in there. It polishes them straight. Delicate things like bryozoans, corals, echinoids like sand dollars, they break up very quickly. More robust stuff like these gastropod snail shells, they stay together for longer periods of time. And again, this isn't dinosaur specific, but think of a dinosaur being transported down the river. Long, skinny bones, ribs, femurs, those will be broken relatively quickly. Jawbones, teeth, those things will be preserved, more likely claws. Hard parts will survive longer. So how do we see anything in the rock record if it's so unlikely? There are these places called Lagerstätten. It's a German word. It means storage place. It's also a mining term for the mother lode. And it's just these rare geologic formations, these rare pages of the rock record that provide higher than usual preservation. So this is the Archaeopteryx, the famous Archaeopteryx from the Solnhofen limestone in Germany. It's a lithographic limestone. A lot of people use it to carve for lithographic prints because it's soft and it's very workable. It was a geologic environment that was very calm, very slow deposition that buried these things without destroying them. And you see Archaeopteryx here preserved with very strong indications of the soft feathers that it had, which is incredibly rare. Finding these things preserved is incredibly rare. These Lagerstätten give us a glimpse at things that are usually not present in the rock record, and they allow us to fill in some of those gaps, like what kind of hair, what kind of skin, what kind of musculature, feathers, details of color and pattern. What color were dinosaurs? What skin patterns did they have? Did they have feathers? If they did have feathers, how many feathers did they have? Where were the feathers? How extensive were the feathers? Was it like birds with massive plumage, birds of paradise with these brightly colored plumes? Or was it more like reptiles that we think about with more scales? So Lagerstätten provide a glimpse into this. So some exceptional specimens are a hadrosaur mummy, the duck-billed dinosaur mummy. This is interesting because it's fully articulated. The entire skeleton is there. You have prints of the soft skin, and it's actually fully articulated. This famous nodosaur mummy, an ankylosaur, it almost looks like this thing just died yesterday. It almost looks like it's alive. There are imprints of the skin. There's actually even imprints of, so we can tell stomach contents even. The bones are all there. There's enough information here to actually be able to perform chemical analyses to get a color. And we know it was darker on the top and lighter on the bottom. This ceratopsian fossil here just made news because it was the first evidence of cloaca, a dino butt. So butts are not preserved in the fossil record. Mostly we're dealing with skeleton. The soft tissues, the muscles, the skin, they go away. Dinosaur cloacas, how dinosaurs excreted, how they reproduced, these things are not often preserved, and so this was big news. Another thing we see here on the tail is preservation of the bristles, these feather bristles, proto-feather bristles, and we also see some carbon film of some of the soft tissue, incredibly good preservation that provides us a glimpse, a very rare glimpse into the soft parts of a dinosaur. And then we even have some skin impressions. So this is a skin impression of a T-Rex. A lot of people are starting to lean towards, well, hey, a lot of birds have feathers, theropods, dinosaurs in particular that gave birth to that line, they have a lot of feathers. T-Rex is on that same line. Did T-Rex have feathers? Well, at least from here, it doesn't look like it. It's scaly here, but just because it was scaly on one part of its body doesn't necessarily mean that it was scaly all over the entire body. Maybe it had like a mane of feathers or like a spine of feathers along the back, or maybe it didn't. We'll talk about that later on in the lecture as well, about how and why we might be able to know. And so the ultimate story here is that the fossil record is really more about the gaps are the rule here, not the exception. And so some apparent jumps in the fossil record from one organism to something that's pretty radical different might be just a result of these gaps. So probably the most famous example of this kind of smooth gradational evolution is the evolution of the modern horse. So this is a modern thoroughbred with the kind of one-piece hoof. Over time in the rock record, we see slow, steady gradation, gradation from a five-fingered, like us, mammal ancestor, and they slowly lose digits until it's a single hoof. There are still gaps in this record. Another good example is the evolution of a whale. So we go slowly from this land-based terrestrial organism that was probably hunting along shores to something a little bit more aquatic that was probably spending significant amounts of times in the water with webbed feet. We can see the transition to this very weird, kind of aggressive, still has legs, but is probably primarily aquatic, if not exclusively aquatic, to a modern whale. And how do we know that this happened? We see these similarities in the bone structure, and we see these gradual changes in the hind limbs. Here, the hind limbs slowly get less and less prominent. How do we know that whales had limbs? Killer whales and all whales have these floating pelvic girdles, floating diminished femurs just floating inside their bodies that tell us that they were the product of a terrestrial ancestor. But there's pretty big gaps in here. And so one of the big arguments against evolution is always, where are these missing links? Where are these gaps? And how do we fill these gaps in the rock record? Well, in a lot of times we can't, because there's so many holes in the rock record, so much geologic time is missing, so much is not preserved. But if we think about it, if we were to find a transitional organism here in between, we've filled that one gap, and now we've created two gaps on each side. Every missing link that we find creates two more missing links. We're never going to have the whole steady progression. Evolution in some cases does actually make jumps, and so maybe the whole progression is not even actually there. So a good example of this is, here's these, I don't know, they're like home plates organisms. One species here kind of maintained over time, was static, and the other species kind of got separated. We'll talk about speciation next week. Over time, they gradually added these tentacles very slowly. And so this part of the rock record here, this slow, steady gradation is gone. It's wiped away. And we're only left with the brown time, where it's all the home plates. And we're left with the yellow time, where we see that these fully evolved 5 septa with 5 tentacles is already there. We don't see the slow, steady progression because it's been wiped out from the rock record. It wasn't preserved. So remember, when we're talking about the fossil record, what is likely to be fossilized, how rare it is that anything's fossilized at all, and how challenging it is to try to reconstruct what these things looked like when they were alive from just the hard parts. So that's all I've got for today. I hope you're enjoying the lectures. I hope you're enjoying the class, and goodbye.